Hello, good morning, and welcome to my talk on the Fuzion programming language. The Fuzion language and its implementation is what I've been working on since about 1 year. During the last couple of months, I was constantly distracted from working on the implementation, though, by our little puppy Ellie. And you will see her popping up in some of these slides, so I hope that she doesn't distract you too much from my presentation. Let me start with giving you a bit of background on myself. I've been working in the area of programming language implementation, compilers and language tools for the last about 30 years, with compilers starting with Amiga, Oberon, Eiffel compilers, a lot of work on Java compilers and Java implementations, and recently the work on the Fuzion language. Motivation for Fuzion is that nowadays many languages, mostly in the object-oriented world, get more and more overloaded with more and more concepts such as classes, methods, interfaces, constructors, traits, records, structs, packages, value types, and so on. And it becomes more and more difficult for the developer to choose for their tasks what of these concepts to use. Fuzion instead comes with one single concept, that of a Fuzion feature, and it relies on the compiler and on tools to implement this feature as efficient as possible, expecting that tools can make better decisions than the developer. Another point of motivation is that systems nowadays become more and more safety critical, so we need to ensure the correctness of the system by analyzing applications with tools, but also by having specific features in the language. I start off with very classic Hello World example, which is straightforward to understand in Fuzion and which shows two of the most important concepts already, which is first a feature declaration. The Hello World example itself is declared as a feature, that is a routine printing Hello World. And the implementation of that routine is the second important concept, that of a feature call. In this case, println is the main feature that is called that prints the Hello World output. There's actually another feature call in this example, which is that to the field standard out, which results in the standard output stream. So let me go into more detail on a feature declaration in Fuzion and what a feature declaration consists of. I'll do this with some pseudo example code implementing a stack in Fuzion to illustrate how the different parts of a feature declaration work. First, a feature needs a name. In this case, this is my stack. Then a feature can have a list of formal arguments and a result type. In this case, there's one formal argument, the maximum size of the stack, and there's no result type. No result type means that the stack instance itself is the result of a call to this feature. So that works pretty much like a constructor in object-oriented languages. Next, a feature declaration happens within the context of an outer feature, in this case myutils, which means that a feature declaration automatically declares a closure of the declared feature and everything that is in the outer features that is also accessible from within the inner newly declared feature. Next, a feature declaration can have a list of formal generic arguments. In this case, the type of elements stored in the stack is given as a formal argument. A feature can inherit from other features, so there's a list of parent feature calls that can be part of the feature declaration. For defining what a feature actually does, a contract can be specified, which means we give a pre and a post condition, where the precondition defines what conditions must hold before that feature can be called. In this case, the precondition is that the maximum size must be larger than 0. And the post condition defines what guarantees a call to that feature gives. In this case, the post condition says that the resulting stack will be empty. Finally, a feature declaration has an implementation which defines what this feature does. So it can contain code that is executed on a feature call, but it can also contain declarations of inner features such as size is empty and push in this example. So here you see an overview of all aspects of a feature declaration. Next, Fuzion contains or provides a lot of syntactic sugar to ease the life of the developer, but this syntactic sugar doesn't complicate the internals of the language, because the syntactic sugar gets mapped down to feature declarations and feature calls. Examples of the syntactic sugars include declaration of loops that get implemented internally as tail recursive features. First-class functions in Fuzion are features that inherit from a standard library function feature. Union types are implemented internally as instances of the standard library choice feature with actual generics, and tuples, very similar, are implemented using the standard library tuple feature, providing actual generics for the different parts of the tuple. I don't want to present all the syntactic sugar here, but I encourage you to have a look at the flying.dev website to play around with that, and I'll give you a short example of what this looks like. So this is the Fuzion website, flying.dev, and there you find a tutorial with lots of different aspects of the language, and you find code examples in there that you can execute in the website, or you can also modify and play around with the code and run that. So back to the slides. A very important aspect in current or many programming languages is the concept of immutability, which means that variables or fields can be assigned a value only once, typically at the declaration of those fields, which is a feature that is great for static analysis and for compiler optimizations, and for multi-threading that becomes race-free automatically. But also, this concept scares many developers, in particular those with a more object-oriented background. Immutability in Fuzion is done in a way that it comes more or less automatically in most cases. So most fields are automatically immutable. The syntax of a field declaration for an immutable field and an assignment of a value is very simple compared to that of a mutable field and modification of such a field. The fact that loops are converted to tail recursive function has the side effect that index variables used in that loop automatically become immutable fields in the tail recursive function without the developer even realizing that. Within Fuzion, fields that are shared between threads must be immutable, and communication between threads is restricted to specific channels. Memory management in Fuzion. I will illustrate this with a small example of a feature implementing complex numbers that consists of a real and an imaginary part. And in this case, this only provides one inner feature, abs, that calculates the absolute value of that complex number. And there are two uses in my example of a complex number. The first is a call that creates the complex number and then calculates the absolute value of that. In this case, everything is happening locally, and the compiler will typically allocate this on the stack or maybe even in registers. While in the second example, if we pass an instance of complex to another feature, it depends on that feature whether this can be allocated on the stack or it has to be allocated on the heap, in case that function receives reference and extends the lifespan of the reference to something longer than the feature call itself, it might be required to allocate that object on the heap. So in summary, static analysis in Fusion detects the lifespan of values, performs register and stack allocation when that is possible, and heap allocation as a fallback. The heap allocation has to be freed, and that will be done by a real-time garbage collector that provides bounded allocation time and solves the memory fragmentation problems. There's actually a lot that I could talk about the implementation of this real-time garbage collector, but due to the very restricted time that I have here, I have to refer you to the abstract and the references in there. Next, Fusion is a statically typed language, so it becomes very important for the developer convenience to have a good type inference system, that you don't have to type the types all of the time. When this happens in Fusion, for example, for the declaration of fields, where the type is automatically inferenced from the expression that is assigned to the field, or for the declaration of a function, where the result of that function gets inferred from the expression returned by that function. And in this example, there could be two different values, a and b, returned by the function. So the type inferencing has to join and build the union of the function to find the biggest possible type both a and b can be assigned to. Next, for numeric constants, the type inferencing happens kind of the other way around, where the type of a numeric expression, a constant numeric expression, actually depends on the value the expression is assigned to. So in this case, we can propagate the unsigned 128-bit type to evaluate this expression without causing an overflow, while if there's no type, there will be a fallback to default integer or floating point types. So in summary, expressions to assigned fields or function results are inferenced from the expression that is assigned to those values, and there's a dedicated phase in the compiler to perform this type inferencing. And this phase actually has to work lazily, iterating through the application, because there can be dependencies of types in a very complex pattern. There could be even source code that introduces cycles in the type dependencies. So these cycles need to be detected by the type inferencing engine and result in a runtime error. No, not a runtime error, a compile time error. Next, for constant numeric expressions, the type is inferred from the target these expressions get assigned to, and if there's no type given for that, a default type is used. The status of the Fusion implementation is that it's still in a very early proof of concept state. There's an interpreter that runs on top of a Java VM, and there's a C code backend that is under development, and the analysis tools are also still under development. So there's a lot of work that still needs to be done. I hope I could spark some of your interest into Fusion, and I would like to guide you to resources related to Fusion. There is the website flung.dev that I've already shown you, and there's a GitHub repository with the Fusion sources. I'm happy to receive any feedback, and there's also a number of ways that you could help that project to get forward. So please check out these resources. Thank you for your interest, and if everything goes well, I think the future version of me will now be available to answer your questions. Goodbye.